Hi everyone. This is a supplementary video for lecture 2. This is the third video. And as you may recall from the lecture that we had mentioned that we will basically try to derive some of the steps that I had skipped over in the class in this video. So as you just to quickly recap, one of the things that we discussed in the lecture was that the conservation equation for a scalar B with a flux F comes out to be this equation where B was the scalar, okay, and then F was the flux of scalar B and BV was the production rate, production rate, production rate per unit volume. Okay. So that was the thing we derived in the class, and then what we did was we substituted for a few cases. So I'll directly jump to case 2, which as you can check from your notes, where B is equal to Ci, or the concentration of the ith species. Flux is equal to Ci times velocity vector V, where V is the, just recall again, it's the mass average velocity, and the flux is minus di grad Ci. And where minus gradient of Ci is because we have already assumed a pseudo binary assumption. So this is the diffusive flux. So this part is the diffusive flux, right? And we've already invoked the pseudo binary assumption because I'm directly writing it as di grad Ci. And also just recall that constant rho is implicit within the pseudo binary assumption that we have assumed a constant rho. Okay. And this constant rho implies that the continuity equation enforces that del dot V is 0. Okay. So we had done this, and then one thing we had also noted was the BV, that we will represent BV as Ri, or some sort of a reaction rate, or basically where a reaction rate is positive for production, negative for consumption, and so on. And now what we will do is we will substitute these terms back, okay? And BV, basically BV will also go here. And then what I will do is I will derive the final equation by following some of the steps, okay, which I had skipped over in the lecture. So let's substitute them back. What we will get is del Ci by del T plus del dot CIV minus DI grad CI is BV, okay? So just to make sure that everybody is following, this is B, this is F vector, and this, this should be Ri here. Ri, and this should be BV, okay? So this is the equation that we can substitute here, put these variations back here, and then we'll get this, okay? Now the main thing that we have to do is we want to open this basically long expression of flux into two parts, okay? So it's simple that whenever you have a divergence operator, you can just simply break it from, addition and subtraction. You can simply go from here to, you can go to this step, del dot CIV minus del dot DI grad CI. Okay, so I've simply broken down the flux term into two parts is equal to Ri. Okay. Now, this DI dot gradient CI is nothing but DI del CI by del X EX plus del CI by del Y EY plus del CI I by del z ez. Okay, let me clean it up a little bit just to make sure the text is clear. Del c I by del y ey plus del c I by del z ez. Okay. Uh, so you can basically imagine that when I'm doing another dot product here with the gradient, and this gradient operator is, as we have discussed before, this is del by del x ex plus del by del y ey plus del by del z ez, right? And we are taking a dot product with this. Okay, so again, just to recap, this is this expression here, and this is here. So when you take a dot product, you basically will multiply this term by this term, this term by this term, and this term by this term. Okay, and this simply becomes, I will simply write this here as, this will become, and we assume di to be constant, and di del square ci by del x square plus del square ci by del y square and del square ci by del z square. So you multiply the x term with the x component, y component with the y component, and z component with the z component, and then you add them. Right? That's the property of a dot product. So this is essentially known as the Laplace operator. Okay, Laplace operator, which essentially means you take a scalar and you do basically the second order derivatives of with x, y, and z, and you sum them up. Okay, so this term here essentially simplifies to this term. Okay, so let's now go to the next step, which is basically we have simplified this term, and we have done del ci by del t plus del dot civ, okay, is equal to ri plus di del square ci. Okay, so this is now you already have the one term in the final solution. We have already have a second order operator here. Now we have to simplify, further simplify this term. Okay. So to basically do this, you need to know an identity. So now what we want to do is we want to have, you have ci and v, and what we want to do is we want to exploit this property that del dot v is 0, because that comes out from the continuity equation, right? To do that, there's an identity, if you're not familiar with it, which says that if I have a scalar a, so this is a scalar here, this is equal to a del dot b plus b dot del a. Okay, so this is the identity of if you have a scalar multiplied, basically it's like a dot product. Oh, sorry, it's like a product rule where you have two terms and you're taking derivatives. So you first basically take with the b, a divergence of b, and then you multiply with a, and then here you have an operator. Basically, you have b dot del first evaluated, and then you apply it on a scalar a. Okay, so let's say a is here, in this case a is ci, and please don't get confused with this b vector. This is just an identity. This is nothing to do with the b scalar that we had initially. And here b vector is v, right? So that I can write this, simply say del dot ci v vector is ci del dot v plus v dot del ci. Okay, and so this is equal to 0 because we know from continuity, and what you get is del ci by del t plus v dot del ci is equal to di del square ci plus ri. Okay, so I hope this is this clarifies what we had done in the class. So I just also derived what is a Laplacian. So when you have a gradient and a divergence of a gradient, you get a Laplacian, Laplace operator. And then we had basically, we simplified this term into two parts. where by you invoking the continuity equation, we can get this result. And just so that we, for completeness, I want to clarify that this basically means Vx del x by del ci by del x, Vy del ci by del y plus Vci by del c. Okay, so this is, I hope this is clear. Okay, so now let's go to the second. We did this for case 2, which was the concentration, velocity. The flux was basically one part was diffusive, one part was convective, and then the reaction rate. And let's do this for case 3, which was case 3. So we had B equal to rho CPT, okay, rho CPT, and we had flux equal to rho CPT V vector minus K grad T, right? This came from Fourier's law because this is Q vector. And then we had BV equal to HV. So now we'll substitute again, substitute back. So we'll get del by del T is rho CPT plus gradient of rho CPT V minus K grad T, okay, is equal to HV. Okay, so we get this. I've just substituted into the equation, substitute in, just to refresh your memory, substitute in del V by del T, del dot F is equal to BV. Okay, so that's all I have done here. Now, one thing we'll do is we say constant CP. So the first thing we do is we say constant CP. Okay. Now, I hope you can all appreciate directly, because from the previous example, that this del dot of T is just simply a Laplacian, okay, because this is a gradient and then there is a divergence operator here. You can see it here again. When we had a gradient operator here and a divergence operator here, we got a Laplacian. Okay, so I'll directly write this as del by del T. I'm taking out Cp of rho T plus del dot rho TV, right, is equal to HV plus K del square T. Okay, so what have I done there? I have taken this term and converted into a Laplacian, and I also have taken it to the right hand side. Okay, and so this is K del square T, which is the Laplacian operator, and then we are left with this term here, and I have taken Cp outside because Cp is a constant. We have assumed a constant Cp. Now, somebody had raised the question in the class, which was an excellent question, is that do we have to assume rho is constant? And I hope you can now see that rho, we do not have to assume rho to be constant. And why is that? Because we can simply say now, I can apply a product rule here. I can write rho del T by del T plus T times del rho by del T, right? This is the product rule. And you can see that there is a rho V vector here, right? So it's a rho V vector here. Let me just write this more clearly here. So I want to apply del dot rho TV here, right? And what I want to do here is I want to be able to write the continuity equation, which says that del dot rho v vector, basically del rho by del t plus del dot rho v vector is equal to 0, right? That's the continuity equation, which is that del rho by del t plus del dot rho v vector is equal to 0. I already see a del rho by del t here, and I see a t times rho v vector. So what I want to get is a del dot of rho v vector. So naturally, I will want to basically write this as del dot of a b vector, where b vector is rho v vector, okay, and a is t. So I'm going back to this identity here, which I had used, del dot ab. So I had used a as ci and b as v vector. That was more obvious here. Here I'm using a as t and b as rho v vector. If you do that, so basically you will get, recall that this essentially means del dot ab is a del dot b plus B dot del A. Okay, so this is the identity. So I can write this now by substituting these two values. I'll get T del dot rho V plus rho V dot del T. Okay, so this is the expression I get for this term. Okay, and now I can substitute it back here. So what I get is plus let me change the color, plus T del dot rho V, okay, plus rho V dot del T, capital T, is equal to HV plus K del square T. So let's just remove this from here for now. Okay, and you get this. So what you can see now is I'll go from here to here. We have Cp rho del T by del T plus rho V dot del T. Okay, this is the first part of the term. The second is T into del rho by del T plus temperature times del rho by del T plus del dot rho V. Okay, is equal to HV plus K del square T. Okay. And you can imagine that this is equal to 0 from continuity. So simply, finally, the rho can also come out from here. So you will get rho Cp del T by del T plus V dot del T is equal to HV plus K del square T. And finally, we get the equation that we have written in the class, del T by del T plus V dot del T is equal to K by rho Cp del square T plus HV by rho Cp. So I hope you can see how we got to this equation, and we did not have to assume the density is constant because we get the full continuity equation when we simplify the terms. And all we did was we use this identity that del dot AB, where A is a scalar, B is a vector, can be represented like this, and that automatically gives you a continuity term in between. So in this video, essentially what I wanted to do was I wanted to derive this equation here. Sorry, not this one. I think it was here. Yeah, this equation here, which we had mentioned in the class, and how we derive this equation using continuity equation, and also the energy equation using continuity equation. And hopefully this helps. Please do let me know if you have any questions, and I look forward to seeing you in the next video.